Hello, AP Statistics. This is Mr. Kim. Today we'll be talking about the last portion of Chapter 4. I'm going to call it 4.2 Experiments Part 2. In the textbook, if you go through 4.3, they're not quite as relevant as one might expect from an AP exam, but all the vocabularies from the 4.2 sections is vital for you to be able to answer questions on the AP exam. Now, on the skew to script, this is now considered 4.4. That's their last thing. So obviously, they also considered it not relevant to the textbook material for 4.3. So we're going to skip that entirely and just focus on this. There are a couple of vocabulary terms that you need to be aware of, and a lot of these are just writing. Before we jump to the main lesson, the new stuff for today, let's kind of go over the things that we talked about from yesterday. So I want to give you guys a problem. I want to talk to you guys about how you might answer a question like this. So you will always be asked to write down quite a bit. This is more of a free response chapter. If anything, for multiple choice, there's no numbers whatsoever. It's all about just how would you design certain things? What's the confounding variables, and what's the how can you make this better, or how can you improve this on this experiment? Observational studies versus experiments and all that good stuff. So the problem here is concussion-related measures improved in high school football players who drank new chocolate milk. Announced a recent headline. In the study, researchers compared a group of concussed football players given a new type of chocolate milk with a group of concussed football players who received no treatment. Explain why it isn't reasonable to conclude that the new type of chocolate milk is effective for treating high school football players with concussions based on this study. Now, there is no set formula for you to memorize. You just have to think of this realistically. If I give half of the group of football players this new chocolate milk who have concussions, they all need to be controlled within that environment, saying that we have, let's say, 50 football players who actually have concussions and 50 players who also have concussions. They're the same, but one gets the treatment and the other does not get the treatment. And we compare the results. Now, in one group, let's say it shows significant improvement on, let's say, concussion and recovery, versus on the not receive treatment section, they don't really actually get that recovery rate. So does the chocolate milk explain it? We talked about this before, that this is a confounding variable. This does not prove that the chocolate milk actually is effective in helping out these football players, because there could be so many other different factors. Maybe they went home and they had this routine exercise. There's all of these other variables that actually helps a player to recover from concussions that doesn't really necessarily have to result from drinking a chocolate milk. To test the effectiveness of the new type of chocolate milk, you recruit 50 football players who suffer concussion in the last 24 hours. Write a few sentences describing a completely randomized design for this experiment. Okay, so even if I want to, let's say, do this with the confounding variable intact, let's say that I want to do a completely randomized design. You always must say that, okay, I'm going to assign numbers 1 to n, randomly assign each football player the number, and then you will randomly select without replacement. And then that will be your 50 football players who is going to, let's say for the first 25 that you pick, they are receiving a treatment. And the last 25 that they don't pick, they are the people that do not receive a treatment. Or you can go like one by other. And so this would be the format of the randomly assigned, let's say, experiments. There is a specific template available for you on 4.3, the skew the script packet. There are a couple of steps. One of them is definitely the 1 minus n. N minus 1. To 1 to 50 numbers. I'm sorry, that's what I meant, not 1 minus 50. But so you assign from 1 to 50. That's always the way that you want to start off your sentence, by saying on the randomly designed experiment. This is the actual answer. So it is possible that the group received a new type of chocolate milk improved because they knew that they were being treated and expected to get better, not because of the new chocolate milk. This is called a placebo effect. We'll go over that later. It's the physiological effect that comes from just knowing that you're taking a treatment, a pill, chocolate milk in this case, and it's not the effect of the treatment. It's just a psychological effect and say, oh, because I drank this, I'm going to get better. That could be a way. That could be the reason as to why these football players might be getting better. Again, it is still considered a confounding variable, but more specifically, it will be a placebo effect. Part B, number the players from 1 through 50. Like I told you before, use a random number generator to produce 25 different integers from 1 through 50 and give the new type of chocolate milk to the players with the numbers. Give regular chocolate milk to the remaining 25 players. Compare the concussion-related measures for the two groups. Obviously, like I said, always must remember that for a completely randomized design experiment, you want to always assign numbers first and then use random number generator to pick first 25, last 25, and get the groups. This isn't a control, let's say, a topic in the textbook. So in an earlier example, we described an experiment in which researchers randomly assigned 101 schools in Kenya to either receive a regular malaria screenings and follow-up treatments or to receive no regular screenings. Explain why it was necessary to include a control group of schools that didn't receive regular screening. So we're trying to figure out malaria screenings assigned to 101 schools. So we want to have, I have to probably go to the earlier example, but the reason why we always want to include a control group of schools that didn't receive regular screenings is because we want to make a comparison, right? Whether versus treatment versus no treatment, how in this regular follow-up screenings, malaria screenings impact the results of the study. What kind of conclusions you can make based on that. So the purpose of the control group is to provide a baseline for comparison. So that is really the main reason. The effect of regular screenings and to follow up treatments, again, just regurgitating the context here. Otherwise, the researchers wouldn't be able to determine if a decrease in malaria rates was due to treatment or some other change that occurred during the experiment. So if you're just comparing the groups, that doesn't actually include a control group that hasn't been impacted by any treatments whatsoever, you can't make a study based upon that, saying that this treatment is effective in, on the malaria rate, because there's no control group. There isn't something where you can compare it to a baseline in which received no treatment. So that is the purpose of having the control group. Now let's go to the main lesson for today. Today, we're going to be talking about a block randomized design. Then we're going to be talking about a matched pairs designs. And then there's a couple of more vocabularies, placebo effect, in which you probably already know, and the double blind and single blind, which is also very, very quick and easy thing. But the main two things we want to talk about is the blocked randomized design and the matched pairs design. Block randomized design is a different type of randomized design. Yes, there's different types to it that assigns the treatments into groups. What do I mean by that is, first of all, let's go over the definition. A block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to treatment. So a block, in a way, is a group, okay? A simple way to put it, it's a group. It's a group of treatment that is imposed that could impact the results of the study. And I'll show you an example of what I'm talking about. In a randomized block design, the random assignment of experimental units to treatment is carried out separately within each block. So for example, let's say that I have this data of group A and group B. So we randomly select different people into group A and group B. And I know that some of these dots are smartphone users. I know that I didn't give you the context, but I'm going to give it to you right now. Some of these dots are smartphone users, and some of these dots are non-smartphone users. Okay, and so we get this data, typing speed. We did this on a human benchmark as well. So on the group B and group A, we get these variability. In terms of how well they did in the typing speed. Now, it turns out that in group A and group B, we see that a lot of people in group A did a lot better versus group B. And so, but then there's also a lot of these commonalities in the middle. So are these two, people who did worse or better are simply due by chance that you pick the better person who's better at typing? Well, it turns out that if I were to group these by the smartphone users versus non-smartphone users in this first graph, you can see that generally a lot of people who actually, or generally the people who uses a smartphone, tended to do a lot better in this experiment or observations. We have gotten two people who have done far better in group A and group B. They're all smartphone users. So generally speaking, if we get this data, it's a little bit, it's not a really great representation of how group A and group B did, because there's also within the blocks, within the groups, smartphone users did a lot better. So how do we account for this? Well, in order for us to do that, the average of the two groups, basically, of the non-smartphone users versus the average of the smartphone users, they tended to differ by certain amounts. So in order to account for, just to get the overall sense of how these groups were doing, you take the data from the non-smartphone users and just keep it the same as before. You can see how those regular navy blue dots are the same from the top graph to the bottom graph. Now, it's just adjusted typing speed. We adjust it so that it actually accounts for the fact that these two are smartphone users and they differ on average from the non-smartphone users. So we kind of want to decrease that amount to match the average of their speed. So we take these two dots and then we shift it left. I think there was no context here, but you can go to the textbook and read it, that the average difference was about 14 or so. So we take this number 40 and then we subtract it by 14, which gets you about 26. We take this number 33 and subtract it by 14, gets you 19. So that is what adjusted typing speed is. But in order for us to think about this in terms of the context of the graph, this is what I want you to visualize. Usually what they'll ask you is, hey, design a block randomized experiment. So for this is a tip, don't mix the language of experiments and the language of sample surveys or other observational studies. You will lose credit. Use a randomized block design to select a sample for the survey. Oh, this experiment suffers from non-response because some subjects dropped out during the study. So language of the experiments and the language of samples and surveys are different. So that is just one thing that I'm putting it out there. But we'll talk about that when we actually do the questions here. So let's go over a problem. Supposedly, let's say I'm trying to do an experiment where we want to see if 4 different types of popcorn, there's a on the microwave, there is a popcorn setting. So if I press on that, the number of unpopped kernels of corn, how many would they be in comparison to, let's say, we want to use, let's say, better to use a popcorn button or the amount of time recommended on the bag. So let's say preferably like 2, 3, or 5 minutes, whatever the recommendations on the bag, which one would be preferred? Now, we can do this in a many different ways. We can, from before on the randomized design, we have total of 10 bags, each of 4 different varieties. So we have 40 different popcorn bags. We can randomly assign from those groups, half of them here, half of them here. Let's see, where we have 10 of each of those groups. We can assign 5 into each of those groups, saying, hey, these 5 will be assigned into a microwave versus this 5 will be on the regular time, like the time recommendation. And then we can compare the results. But the problem for that is that there are different types of popcorn as well. There's butter, cheese, natural, and kettle corn. So if I want to describe a randomized block design for this experiment, here's how I would do it. I'm going to just give you the answer. Form blocks based on variety. So we have these 4 things, butter, cheese, then we have natural, and kettle corn. So then what we're going to do is we're going to assign, obviously, randomly 5 into each of those categories. So 5 butter into microwave setting, 5 butter popcorn into a time recommended settings, and then we'll just get the results from that. And so because the number of unpopped kernels is likely different by variety, randomly assign 5 bags from each variety to button treatment and the time treatment. And by placing all 10 bags in a particular variety in a large box, shake the box, pick 5 bags without looking, and assign them to be popped using the popcorn button. So here, it's all good. So we assign 5 in each groups. But you can see just how much the description that the AP people are looking for. So you want to assign 5 bags into this, into that. How are you going to do that? You need to tell them specifically the steps that, hey, I'm going to put all these 10 bags in a bag, and then I'm going to randomly pick 5 bags, and then that will be assigned treatment A versus treatment B for the rest of the bags. The remaining 5 bags will be popped using the instructions on the bags. Repeat this process for the remaining 3 varieties. After popping each of the 40 bags in a random order, count the number of unpopped kernels in each bag, compare the results within each variety, then combine the results from 4 varieties after accounting for the difference in the average response for each variety. So what we're going to do is we are going to have these 5 here, then we're going to have these 5 here, and then we're just going to compare the results, right? So these will be the microwave settings, and then we want to get all the results here. Oh, that should not have happened. And then kettle corn, and then versus the other group that actually just gets timed. So if we just group this A, B like this, then we compare all these results from A's, and we combine all of these results together, and then we get the treatment A, the microwave setting. And then versus group B, the rest of them, we want to compare those results and say that this is timed. And then we're after we compare the averages of those 2 groups, then we make some adjustments to the settings, and then that will be the randomized block design. The end result product in terms of graph, that's not what they're asking you to do. They're asking you to simply design and account for the steps in which how this is going to occur. So if you take a look at here, the way that they said it was after they, have the bags popped, their count the number of unpopped kernels, and then it says compare the results within each variety. Then combine the results from the varieties after accounting for the difference in average response for each variety. So we want to make sure that we compare the results, finding the averages, and account for the differences, and so we make the adjustment. So this is all they're going to say for the very last sentence. After you say that, it should be pretty much okay. Part B, explain why randomized block design might be preferable to a completely randomized design for this experiment. So why do we want to use block instead of just using a regular plain old randomized experiment? Is that randomized block design accounts for the variability in the number of unpopped kernels, again, regurgitating the context here, created by the different varieties. So this is another accounting confounding variable, if you will. If their varieties has an impact on the number of unpopped kernels, which I'm sure it will be, that is something that you want to account for. So you group them by varieties and then make conclusions based on that. This makes it easier to determine if using the microwave button is more effective for reducing the number of unpopped kernels. In a way, block design is to be there to account for these confounding variables, to mitigate them, so that we only just want to solely take a look at the cause and effect being the microwave button to the number of unpopped kernels. Okay. So that is the reason for the block random design, and you want to use this for this particular experiment. Match pairs design. Match pairs design is, in a way, it's quite simple. You're basically giving 2 treatments in a single experimental unit. So the actual definition is a common experimental design for comparing 2 treatments that uses block size of 2. In some match pairs design, 2 similar, very similar experimental units are paired, and then 2 treatments are randomly assigned with each pair. In other words, each experimental unit receives both treatments in a random order. So again, going through this is not really enough. Let's go through an example. So a consumer organization wants to know if using a certain fuel additive increases the fuel efficiency. So you're adding this fuel additive to a car, trying to see if this treatment improves the fuel efficiency. I have 20 cars available for testing. Design a random experiment, or design an experiment that uses a match pairs design to investigate this question. Explain your method of pairing. So a match pairs design, it means that you have a single experimental unit receiving both of the treatments, and usually it's going to involve flipping a coin. I think it should be here. Yeah, flipping a coin. So if you have a car, let's say, and you have a fuel additive that you want to add, and you want to compare the results before and after. You want to give each car both of the treatments and compare, because we want to eliminate for the fact that we have two different cars. Maybe for this one specific car, it has a better fuel efficiency, or it can actually have a better impact by having that fuel additive added. We want to eliminate all those confounding variables. So we want to experiment on single cars alone, each of those 20 at a time, but we impose both the treatments onto that single experimental unit. That's the matched pairs design. In a way, it's like matched pairs on a single experimental unit, both of the treatments. So it is reasonable to think that some cars are more fuel efficient than others. Like I told you before, that's the confounding variable. So using each car as its own pair accounts for the variation in the fuel efficiency in the experimental units. All that's saying is that we want to eliminate all the other, factors that involves improving fuel efficiency for each car. So we want to use only one car at a time. For each car, randomly assign the order which the treatments will assign by flipping a coin. So when you get heads, let's say, when you get heads for the flipping the coin, you receive the fuel efficiency on the first week. Okay. So first week, you get the fuel efficiency added, the fuel additive added, and you measure the fuel efficiency for the first week. So this is treatment imposed. And on the second week, you don't get that treatment. So during those days, when the fuel additive is not added, how is it going to run? If a different car, let's say this is car number 1 and this is car number 2, car number 2 gets a tail. That means in the first week, that specific car gets no fuel additive whatsoever. And after that, let's measure the fuel efficiency. Then on the second week, they get the fuel additive added. How is the fuel going to run now? What's the fuel efficiency? Then you compare the results from that. So heads indicates using the additive first, no additive second, tails vice versa. For each car, record the fuel efficiency after using the treatment. That's match pairs design. You always want to involve something called flipping a coin, because there's always going to be 2 treatments imposed, and is always equal to 2, not the sample size, but the treatment size. Like if you want to think of it that way. So matched pairs, pairs of the experiments done on one single experimental units each time. If you watch the Skew the Script video, they also talk about this as well, where they want to make some conclusions based on a study of depression, and they give fake pills to the subjects, but each subjects are their own groups. So a subject flip a coin, let's say heads, they receive this fake pill on the first week, and then they don't receive anything on the second week. And they measure their, depression based on asking questions, how they feel about certain things. So if you read this description here, for each subject, flip a coin. Heads indicate they get the fake pill. Remember, it's a fake pill for the first week and no pill for the second week. Why they did this experiment, just, look at the video and see they're really trying to experiment whether the depression can be treated by these fake pills using something called placebo effect, which is a psychological effect by taking the pill in your mind, saying that, is that enough alone to help you treat for the depression? Tails indicate the opposite treatment order. Have each treatment fill out depression questionnaire, undergo a PET brain scan, and see how they do. So yeah, that's the match pairs design. But since we're actually on this subject, if we have a belief in this pill causing a biochemical change based upon this fake pill, but the fake pill doesn't contain any sort of treatment for depression, it's just there's nothing in there. So if a subject has shown a significant improvement in a PET scans, depression and how they do, that's all placebo effect. Placebo effect describes the fact that some subject in experiment will respond favorably to any treatment, even an inactive treatment. So it's like a fake pill, for example. This could create a psychological effect. Oh, I am taking this pill so that I must be getting better. That kind of a mindset in your mind helps you to improve on a physiological basis. And so it's not really due to the pill, rather it's due to the mind. So we want to eliminate those things for placebos. A lot of medical trials has to eliminate for the placebos in order for it to be proven effective and get FDA approval. So this is type of things that you want to take into account for if you're doing a medical experiments or anything that deals with human life, to improve on whatever the diseases or psychological mental disorders that they have. They need to always account for this. The last thing that we're going to talk about is a double-blind and single-blind experiment. To be blunt, I'm just going to describe to you guys what this is talking about. Double blind is neither the subject nor the people who's actually imposing the experiment do not know, measure the response variable, know which treatment the subject is receiving. So we usually, the people in the lab coach knows what they're doing, and oh yeah, this group is receiving this group is receiving that. However, in a double blind experiment, it's double blind because the subject and the experimenters, they both don't know what's going on. They both don't know what type of treatment they're imposing. Why would you want to do a double blind experiment? Well, that's just so that you can eliminate the bias from the experimenters. If you think about it, if the experimenter in some ways wants to have created this drug, if it's a drug company and they want to do an FDA approval, they want to do a test. So they, do experiments, they get people into groups. But why do they want this to be double blind? Is so that they don't have a favorable gearing towards this specific group showing improvement versus non-improvement. Okay, so it's in order to eliminate the bias from the people who's actually imposing the treatment. That's why you want to have a double blind, so that they don't give any favorable bias towards this group. Oh, maybe they received more dosage, maybe they received more, they picked the group that actually will show a favorable outcome versus a group that will not show. And then they can't really base a conclusion based on a study because it's biased. So double blind is there to eliminate that. A single blind is there so that we can eliminate the confounding variable from the experimental units. The subjects don't know, but the experimenters know. So either the subject or the people who interact with them and measure the response rate don't know which treatment the subject is receiving. So the person who's actually receiving the treatment, they do not know what's going on, but then the experimenters will know which treatment that they're receiving. So in order to eliminate the confounding variable for the experimental units, we want to do a single blind experiment. To wrap up today's video, let's go over a problem. So early research showed that the magnetic fields affected living tissue in humans. Some doctors have begun to use magnets to treat patients with chronic pain. Scientists wondered if this type of therapy really worked. They designed a double-blind experiment to find out. A total of 50 patients with chronic pain were recruited for the study. Doctor identified a painful site on each patient and asked him or her to rate the pain on a scale from 0 to 10. Then the doctor selected a sealed envelope containing a magnet at random from a box with a mixture of active and inactive magnets. Then the chosen magnet was applied to the site of the pain for 45 minutes. After being treated, each patient was again asked to rate the level of pain from 0 to 10. So a lot of things in here in this experimental design. We want to have inactive magnets to, again, this is a experiment based on human life and improving human life. So we want to account for the placebo effect. There's also a group of people. We want to use double blind. We're going to talk about why it's important for it to be a double blind here. Explain what it means for this experiment to be double blind and why was it important for this to be double blind? Here's the answer. So neither the subject nor the doctors applying the magnets and recording the pain ratings knew which subject had the active magnets and which had the inactive magnets. They don't know. The subjects are just the one that's receiving, and the doctors are just imposing the treatment, receiving, imposing treatments without knowing anything that they're doing. Like I mean, obviously they know that this is not going to kill them, but they are not given the forefront of what this experiment will entail. They're just asked to do this, and so they're just doing it. If subjects knew that they were receiving an active treatment, again, that's placebo effect. They will think that it will, it will improve their body based upon whatever the treatment they're receiving. Researchers wouldn't know if any improvement was due to the magnets or to the expectation of getting better, the placebo effect. So to account for that, you want to make sure that none of them know what treatment that they're receiving. If doctors knew which subject received which treatment, they might treat one group of subjects differently from the other group because they want to say, hey, this magnet really improves, or they want to get a better funding for their research grant or whatever. There could be so many human reasons or greedy reasons for them to actually favor one group or the other. It happens all the time. So this would make it difficult to know if the magnets were the cause of any improvement, or it's simply due to the fact that the doctors really want this research to be proven effective and known to the real world. So in order to account for that, we want to use the double blind study. Okay, so today you have the Desmos activity, Desmos classroom and all that. So after you finish that and also watch the video, next week I will assign you some questions from 4.2. And after that, I will give you some reviews and we'll most likely take test next week on chapter 4. So please keep that in mind. I know that it's going to be it hasn't been a long chapter, but also at the same time, there's a lot of things that you need to know how to write. It's not really going to be mostly multiple choice. Rather, it's going to be more of a writing situation. So read the textbook, read the notes, and try to see what they're looking for. You don't need to write down this word for word. Rather, you need to know what's essential and the key points, takeaways that you need to have in order to get a 4 on the AP exam. All right, so thank you so much. And I will upload another video next week regarding the reviews. Have a great weekend and I'll see you next week.